Hello and welcome to this video on using Maxima for some basic three-phase calculations. This video isn't a three-phase tutorial in its own right. In fact, what we're going to do is revisit some of the calculations that we performed by hand, as it were, in some of our previous videos, but we're going to see how they can be calculated in Maxima. This video assumes that you've already got a basic familiarity with Maxima, but even if you're brand new to this software, you should be able to follow along. So one of the first things we're going to do in this video is actually define a function. And the reason we're going to do this is because Maxima tends to work in rectangular form by default. When we're performing our calculations, Maxima prefers to use its calculations in what we would call rectangular or Cartesian form. But a lot of our answers we might wish to present in polar form. And so one of the first things we're going to do is we're going to create a function which converts a answer or a result that's in rectangular form. It's going to convert that into polar form. So just to begin, I want to start by a bit of an example and show two functions that are already built into Maxima to calculate properties of a complex number in polar form. So to do that, I'm going to create an example of a complex number. I'm going to call it Z. And let's say that Z is equal to 4 plus J3. So 4 plus, and J in Maxima is given by using the percentage symbol. Percentage I, so percentage I for that J term or I term, depending on which that you use. But 4 plus J3 is going to be 4 plus I times 3. Remembering that in Maxima, any multiplication needs to be explicitly stated, so we need that multiplication in there as well. And what I'm going to do is, rather than ending that statement with a semicolon, what would happen is if I execute that, we would just see that same result repeated back to us. Really, I don't need to see that. So rather than a semicolon, I'm going to end that in a dollar symbol there, and then when I press Shift and Enter to execute that, we don't see anything. That's an example of what's called a suppressed output. So it's still stored that complex number. It's called it Z, and we don't see the result. If, on the other hand, I was to ask for Z and just type Z there and execute that, then we get our result. So Maxima knows that we've defined Z as 4 plus J3. But what I want to do is I want to introduce two functions that are built into Maxima. The first one is carg. No, it's not actually. It's cabs. C-A-B-S. And what that is the absolute value of a complex number. So the C for complex, ABS for absolute. And what I'm going to do is I'm going to ask for the absolute value of Z. And what I'm going to see is the result of 5. So what Maxima has done here is, if we're familiar with complex numbers, we have a real term of 4. We have an imaginary term of 3, or J3. And by using a bit of Pythagoras' theorem, we can do 4 squared plus 3 squared gives us the absolute value squared, or the magnitude squared, and the square root of that is 5. And so it's kind of done that all for us using this cabs function. The next function that I want to mention is one that I just said before. It's this carg function. And again, same idea. It's for a complex number. It gives the argument of that complex number, or the angle of that complex number. And so again, I'm going to do carg of Z. And as a result, I get something that looks like this. It's the arctan, or tan to the minus 1, of 3 over 4. And again, sort of recalling that, if we can visualize that triangle that goes along 4 and up 3 in the complex domain, we've got this sort of hypotenuse. The angle of that hypotenuse from the real axis, from the horizontal, is going to be tan to the -1 of the opposite over the adjacent, in other words 3/4. And so what we've got here is Maxima doing that. It's working out tan to the -1 of 3/4. Now that, as it stands, is a bit unhelpful if we want a numerical result. And so what we can do if we want is we can append the function numer, N-U-M-E-R, on the end there. And if I repeat that again, then it's going to give us a numerical value. One other thing to mention is that this numerical value is in radians. And what we're going to do actually is part of our sort of polar form results, we might want to see them in degrees. And so one last little modification we can make here is to multiply this by a factor of 180 over pi. And when we do that, again, pi has that percentage symbol before it because it's one of these sort of built-in symbols, 180 degrees over pi. And when we execute that, we get this result of 36.87 degrees or thereabouts. So we've converted there from radians to degrees. So what I want to do is really create a function that is going to do all of this for us rather than typing in cabs and carg and all that kind of thing every time. I want to create a function that is going to do this for us automatically and not have to worry about doing these sort of separately every time. So the way that we're going to do that is we're going to use a particular syntax for defining a function in Maxima. Our function has a name. I'm just going to call it function name for now. I've created this is just a text cell to type in plain text here, just for example. But we have a function which I've just called function name here. That function has an argument. In other words, what that function is going to act on. And when we define a function, we use the colon equal symbol. So rather than when we sort of define a constant, here we use a colon. If it's an equation, we might use the equal symbol. Here, when we define a function, it's colon equals. And then on the right-hand side, we have whatever that function is with respect to the argument. We'll see an example in just a second. Again, I'll use a dollar symbol on the end when I create a function, just so that it's not repeated back to us. So what we're essentially creating here is a rectangular to polar converter. So I'll create a little heading here. So this is our rec to pol converter function. And again, we're going to use this same syntax. So the function name, I'm going to call it pol when we're converting to polar form. And the argument here, I'll just call it rec. So whatever number is we have in rectangular form is going to be what the function pol acts on. So rec could be anything. It could be z, we'll use it as an example in just a second, or any other number. We're going to get its equivalent in polar form. Colon equals. And what I'm going to ask Maxima to do is I'm going to ask it to create a list. So a list is in square brackets. And our list is going to have only two things in it. It's going to have the absolute or the magnitude, and it's going to have the angle or the argument. And we've already sort of spoken about these two things. We're going to do the same thing again here. We've got cabs, and it's going to be cabs of rec, because rec is the argument in this case. So cabs of rec, so we're saying whatever rec happens to be, we're going to find the absolute of rec. It's a list, so it's separated by a comma. We're going to find the argument of rec. Again, I want it in degrees in this case, so I'm going to multiply by that factor of 180 over pi. If you want your result in radians, you can just leave that out. And again, I'm going to stick that dollar symbol on the end there. So when I define that, or execute that, again, we don't see anything, but we've got that Maxima sort of defined that function in the background for us. We can sort of demonstrate that that's the case, hopefully, if we say pol of z. Well, we already know that pol of z in polar form is going to be hopefully 5 at an angle of 36. Let's see if that's the case. We get something that looks like this. Again, notice we've we need to append that numa statement if we want a numerical result. So there we go, we've got 5 at an angle of 36.87 or thereabouts. So our function works. That's hopefully useful to you. What we're going to do is we're going to park that for now, this pol function, but we've defined it. We're going to come back to it later. Okay, so now that we've defined that function, again, we'll come back to it and use that function hopefully later on. But let's get into the first example, and this example is of an unbalanced star network. And again, this is just a repeat really of work that we've done before in a previous video, but we're just going to sort of repeat those calculations in Maxima and hopefully get the same results. So just as a very quick recap, though I don't want to go into the theory here too much, the idea was that we have 3 voltages here, which were defined below. We've got 240 volts at an angle of 0, minus 120, and plus 120 degrees respectively for V1, V2, and V3. And then we've also got 3 impedances, Z1, Z2, and Z3, and they were defined as 4 plus J2, 3 minus J3, and 5 plus J or J1. And the idea being that we calculated the currents in each phase using these, and then we added those currents together to work out the sum current that goes through our neutral or star point as a result of the addition of all those separate phase currents. So in our previous video, this was exactly the same example with the same values and everything like that. We're going to perform it again here. So first of all, again, I mentioned at the start, Maxima doesn't really agree with polar form in this kind of notation here with angles in degrees. There's a few ways we could input those into Maxima, but the easiest way probably is to use exponential form. So what I'm going to do is define V1 rather than 240, well, at an angle of 0, first of all, is just a real number. So I can just say 240 there. And again, I don't want to see it repeated back. So I'm just going to put that dollar symbol there. V2, on the other hand, which is 240 at an angle of minus 120 degrees. Well, 120 degrees is the same as 2/3 pi radians. So 180 degrees is pi radians, and 120 is 2/3 of 180. So what I can do is I can define this in exponential form. We have a separate video on exponential form if you're not sure. But I'm going to say that that's the same as 240 multiplied by e to the power of, or exponential, we can use the exp function, e to the power of minus 2/3 times pi times the imaginary constant j or I. Again, I'm using percentage pi and percentage I for those terms. So minus 2/3 pi j is what I have here raised as a power of e. Similarly, V3 is exactly the same, but it's plus 220 rather than minus 120. I'm just going to copy and paste that below, and I'm going to take the minus out. So we've defined V1, V2, and V3. You might not be sure about whether you agree that these are the same as these, but here's a good opportunity to test that pol function. If we do pol of V2, we get 240 at an angle of minus 120 degrees. Or we can do the same for V3, 240 at an angle of plus 120 degrees. So it's a good opportunity to test that function there and make sure that we've not made any mistakes typing that in. We'll get rid of that for now though. Similarly, we're going to define Z1, and Z1 was 4 plus J2. Well, again, I'm using percentage I for J, and that multiplication has to be explicit, so it's multiplied by 2. So 4 plus J2. Z2, we're saying, is 3 minus J3, 3, so percentage I multiplied by 3, and Z3 is 5 plus J, or percentage I. And I'm pressing enter just to move on to a new line here. Make sure each one terminates with either a semicolon if you want to see it back, or a dollar symbol, else it'll be all interpreted as one big definition here, which we don't want. We want these separately. But I'm pressing Shift Enter then to evaluate all three. So now we've defined V1, V2, V3, Z1, Z2, and Z3. So what we said previously was just a case of using Ohm's law to work out the currents in each phase. We can say that I1 is going to be equal to, I'm using, again, I'm defining it, I'm calling it I1, so I'm using the colon symbol. I1 is going to be V1 over Z1. Let's do all three actually. I2 is V2, V2 over Z2, and I3 is V3 over Z3. Okay, now notice I've ended each of these statements with a semicolon. It doesn't matter if they're all on the same line, they're going to be treated separately because the semicolon terminates each one. But what I see is something that looks a bit like this. What we have is a sort of expanded form here where we've literally just in Maxima divided. There's our voltage on the top, there's our impedances on the bottom. We're getting something that isn't particularly helpful. And so what I want to do in this at this point is introduce a new function which is going to present our results in rectangular form if we want. I'm going to change all of those to dollar symbols because I don't really want to see that. The function that I want to introduce is called rect form, which basically tells Maxima we want to see it sort of nicely put in rectangular form. We want a real term, we want an imaginary term. And so I'm going to ask for a rect form of I1. And we see something that looks a little bit nicer. We've also got that function pol that we've defined as well. So we can ask for the pol I1 in polar form. And we see something like that. Again, not forgetting to append that number if we want to see it as a decimal. So we can do the same thing for pol I1. We can do the same thing for I2 and I3. So I'll just copy and paste that a couple more times and we'll change those. And here are our terms for I1, I2 and I3, those three phase currents in polar form if we want to see them like that. Or we could have asked for in rectangular form I1, I2 and I3. Again, we might want to append that numer as required if we want to see things in sort of rounded decimal form. Maxima will use sort of precision where possible and avoid rounding things, but if we want to see decimals like that, we'll use that numer as and when required. So what Maxima is doing here is displaying things rounded as decimals, but I'm not defining them like this. Notice I1, let's change one of these back to a semicolon. I1 is still recorded as this sort of precise rational number here, using integers where possible. We're only rounding it when we want to see the final result. So it's a good idea to preserve Maxima's definitions in the form of rational numbers there, and only convert them to polar form at the end like we've done here where we actually want to see the result. So I'll give you an example of why that's useful. Rather than using these to work out the neutral current, we could even get rid of these if we wanted to. We're going to use these original definitions here. We're going to say that IN, the neutral current, is equal to I'm not going to use in actually because that's already a function. We're going to use I_neut for the neutral current. We're going to say that that's I1 plus I2 plus I3. Again, I'll leave it as a semicolon for now. We'll see we get something like this because Maxima isn't prepared to start rounding things and converting them to decimals unless it needs to. I'm going to change that to a dollar symbol. We don't want to see something in that form. We would like to see it either in rectangular form. So rect form, I_neut numerically, we'll get something that looks like that. Or pol, the function that we defined earlier, of I_neut, again, numerically. And we see something like that. Hopefully, if you've seen our previous videos as well, you'll see that these results correspond with what we found previously when we sort of did those calculations manually. Here's another example for now an unbalanced delta network. Again, this is from a previous video. And what we're going to do is we are going to perform some of the same calculations that we did previously. Just as a very quick recap, what we did was we calculated the phase currents flowing through each of the phases in the delta arrangement, and then we calculated line currents by using the differences between the phase currents, because we have these sort of opposing junctions where I12, for example, is flowing that way and I31 is flowing that way, and so I1, which sort of approaches that junction there, must be equal to the difference of these two currents. We'll go into more detail in the previous video, but we're going to just sort of repeat those calculations here for example's sake. So what we're going to do first of all is define some voltages. I want to use the same voltages as we did in the example, and we said that V12 is equal to 415 at an angle of 0, which is just 415 in our case. V23 was equal to 415 at an angle of minus 120 degrees. Well, again, we're going to do the same thing here. We're going to use that exponential form, and we're going to say that that's the same as minus 2/3 times pi times j, or percentage I. And V31 was exactly the same idea, but plus 120 degrees. 415 at an angle of plus 120 degrees. I'm just removing that that minus there. So again, let's just test that I've done that correctly. We can do pol V23, and we get 415 at an angle of minus 120. I can do pol V31, and we get 415 at an angle of plus 120. So we're happy there. Similarly, Z12, we said in the previous example was 4. This is from the previous video rather. In this question, Z12 was 4 plus J2, so 4 plus I times 2. Z23 was 3 minus I times 3. And Z31 was equal to 5 plus I times 3 as well. In fact, I think they are the same on the 4. Where do we have them? 4 plus J2, 3 minus 3, 5. So they're exactly the same, actually. One thing I will point out, actually, is notice that rather than Z1, Z2, Z3, they are called something different. If these were different terms, it's a good idea to come up with some unique term so that Maxima is not overwriting your previous definitions with new ones. As it happens, because the first one was a star network, Z1, Z2, Z3, rather than in the second example we have a delta network, Z12, Z23, Z31. These are different definitions, but just something to watch out for, that you're not accidentally overwriting previous definitions in Maxima. Anyway, we'll shift enter for there. So we've defined V12, V23, V31, Z12, Z23, Z31. Similar to the previous example, we're going to determine some phase currents, I12, I23, and I31. And we're going to again use Ohm's law there. So we're going to say that I12 is V12 divided by Z12. And again, I23 is, notice I'm using the colon rather than equals here. I23, we're defining that as a colon as V23 rather divided by Z23, and I31 is V31 divided by Z31. Again, just for example's sake, I've left all of these semicolons. We're going to see a bit of a mess here because Maxima has kept everything as integer terms where possible. I don't really want to see that. But again, what we can do is we can see Paul I12 numerically. And we could do the same thing for I23 and I31. These phase currents, though, I'm not too bothered about, because what we said was we were going to work out the line currents as the differences between the respective phase currents. And so what we're going to say, and this we sort of covered this in a previous video, we said that I1 in this case is going to be I12 minus I31. We said that I2 was going to be I23 minus I12. And we said that I3 is I31 minus I23. And you can see for yourself there why that's the case. So I2 is equal to I23 travelling away minus I21 travelling in that opposite direction there to meet at that junction. I3 is I31 travelling in the same direction minus I23 travelling towards it. And so we get these differences here. Again, we go into more detail in that previous video. I'm defining those. Again, I've suppressed the outputs in each case. I don't really want to see them because it's going to be a bit of a mess. I would rather see in polar form I1 numerically, and I'm going to copy that and paste it a couple of times. I want to see I2 and I3. These are our line currents, I1, I2, and I3 that we've calculated with those differences. We're going to see all three of those in polar form. And so in the previous example rather, we had to work these out in rectangular form, then convert them to polar form. Here we've been able to sort of jump straight to the result using Maxima. The last example that we'll go through here, again from a previous video, was when we looked at neutral displacement, and when we've got what we call a floating neutral, or an unknown value for the voltage at the start point at the load here, when there isn't a neutral connection between the source and the load. So one of the things that we did was we discussed using the admittance and or calculating the admittance and using the admittance in Millman's theorem to calculate the value of the voltage at this point. And again, I'll not go too much into the theory here because I'll be repeating the previous video, but we're going to use the same the same idea here, but we're going to use Maxima to perform those calculations. So one of the things that we're going to do actually is we're going to use exactly the same values that we defined at the start. And again, another advantage of Maxima is that we've already defined, where do we have it, V1, V2 and V3 for our star network, and Z1, Z2 and Z3. We're going to use these same values, and we used the same values in the previous video as well. So rather than in the first example where we had a neutral connection, now we don't. And what we did was we calculated the value of this voltage here using Millman's theorem. To use Millman's theorem, the first thing we had to do was we had to calculate the admittance of each phase. And we said that the admittance of each phase we called Y. I want to call it Y1, Y2 and Y3. But we said that the admittance Y is basically 1 over Z. And so Y1 is going to be 1 over Z1. Again, we get something that looks quite literal. Maxima's just done 1 over, and this was what we defined as Z1. It's not done any simplification or evaluation because it would keep it like this for precision. So I'm just going to put a dollar symbol there, but I'm going to do the same thing twice more. We're going to say that Y2, the admittance of Z2, is the inverse of Z2, 1 over Z2, and Y3 is 1 over Z3. So again, dollars for each, so we don't see anything here. But what we can do, if we want to see those, we can use rect form. We can see Y1 in rectangular form, so it's the real term is 1 over 5, or a fifth, minus j over 10, or 1/10 j. We can see that in rectangular form if we want. We could convert that to polar form using the pol function. So pol of Y1. Again, appending that numer to see it in numerical form. But we can easily calculate these admittances, which took quite a while actually to do by hand. In the previous video, we can see that we've done that in a single line here. We've got these results for Y1, Y2, and Y3. Millman's theorem looked something like this. It was to say that Vn, this is the value of voltage at that neutral point here, Vn, we're going to define as, again I'm using a colon here, a fraction with a top and bottom. So I'm going to sort of put these both in brackets just to make it a little bit visually clearer. We said that it was V1 times Y1 plus V2 times Y2 plus V3 times Y3. Now, I don't need any extra brackets here because Maxima's evaluating multiplications before it does the additions, the order of operations. So it's multiplying those, multiplying those, multiplying those, and then adding them together. Whereas if that wasn't the case, we might have to, if we wanted to sort of evaluate things in a different order, we'd have to explicitly put some brackets in. But for our purposes, that's fine. And the bottom of Millman's theorem was just Y1 plus Y2 plus Y3. And again, if we sort of execute that as it stands, it looks like an absolute mess. I don't want to see that. Rather, we'll ask for it in rectangular form. So rect form of Vn, we'll hopefully see something that's a little bit tiny. No, we don't. But what we can do is append that numer statement again, and then we've got our result nicely in rectangular form. We've got a real term and an imaginary term there. Again, if I want to do that and see that in polar form, so pol of Vn, again, not forgetting that numer statement on the end, we get 104.5 at an angle of minus 38.49. And if you sort of return to our previous example as well, that sort of corresponds with what we got last time. Using that neutral voltage there, Vn, we then said that the actual voltages across each of these three phases would be the differences between the phase voltages with respect to that voltage at the neutral point there. And so what we'd call V1 dash, the voltage across this phase we'd call it V1 dash in a previous video. I'll call it V1N in this video, just to avoid using dashes. V1N we can say is V1 minus Vn. So in other words, the voltage across this phase here, V1N, is the difference between V1 and the neutral point. It's the potential difference between the two. And likewise, V2N, we're going to say is V2 minus Vn. And we're going to say that V3N is V3 minus Vn. So we've defined those three phase voltages there across each of these three phases. And again, we can see those in polar form. Polar V1N, Numa, I'll just copy and paste it, polar V2N, polar V3N, and we get those three voltages there with respect to that neutral, that displaced neutral that we calculated earlier as well. So I hope this video has been helpful. We've not gone too much into the theory here. If you're not sure about what I'm talking about in terms of displaced neutrals and stars and deltas and things like that, I would go back to the previous videos, but this has just been an example of how we can use Maxima to perform this, these sorts of calculations much easier and much more time efficiently than we saw in the previous videos. It's a good idea to understand how to work these out by hand, but even if it's just to check your answers or to make sure that you've not gone off on the wrong lines or something like that, then Maxima is really useful to evaluate the results very efficiently as well.